Okay, so I'm greatly honored to be here. I'm not an academic, dropped out of high school. I'm actually here because Jed met my daughter.
Sure.
And
Your sister.
And my sister. But England is sort of part of my family background, and so I'm going to sort of bless this meeting, which I think is very important, with sort of the wisdom of our ancestors. And of course, the greatest among them being Leibniz, who really set the whole stage for this whole thing of realizing and articulating in a very technically brilliant way that binary arithmetic would be the common language of the entire planet, and made that very specific, actually inventing what the shift registers by which all our computing, all our data exchange, every frame of the internet runs through shift registers, and he explained that. But he also warned us about this very problem that we are in today, the sort of state of emergency, that he didn't do this for the people selling oil and sardines. And that's, I'm going to give you the solution first, which is advertising. That is what has ruined the internet. It's what Berners-Lee warned us against. Don't let the advertisers, because that short circuits the whole process, and that's really the origins of our mess. So with that out of the way, here in Britain, we, and I could speak as a quarter Englishman, we were the pioneers of what now is the new thing, deep learning. This is 1958. And it's all here. I mean, pandemonium, which was a method of pattern recognition when you can't specify even the problem in advance. You sort of find out the answer before, without having to explicitly code the problem. So all the levels of deep learning are there. And also the fact that you have to let this go out to the forces of natural selection so it can self-improve. And Jack Good, who worked with Alan Turing during the war, saying that and this also I think justifies some of the predicament we're in, that if you build with initial randomness, then your system contains every network that will ever be required. That's how we get our brains. There's an immense number of neurons, and we prune the connection. So that's what some of this chaos, where there's all this mess, that's what we can hope for, is that it prunes down to something that works better. Jack Good came up with the idea of a ultra-intelligent machine, which he defined later as a machine that believes people cannot think. And this is from a 1980 paper, which is the classic problem. The editors absolutely eviscerated his manuscript and took out all the good stuff. And he gave me, before he died, the original manuscript, which is very much worth reading for the people in your field, particularly I think in the funding field, because he goes deeply into the sort of Bayesian probabilities of how you can, how do you value the payoff in the future in the present. And that came from this book, which really the co-author is Alan Turing. This is how they broke the Enigma codes during the war using Bayesian probability, but of course they couldn't talk about it. That was sort of a trade secret. So the founders were, of course, Alan Turing, who wondered whether machines could think, and Johnny von Neumann, who had sort of another question: how do machines self-reproduce, which is also the world we're in now, where we're sort of machines are reproducing faster than we want them. Claude Shannon, who wondered how machines would communicate and made that mathematically explicit. Norbert Wiener, who dealt with the question of how machines would take control, which of course we also accept that they are now doing. And then our patron saint, Louis Fry Richardson, who believed that machines would predict the weather, not only believed it, but showed by hand how to do it in 1922, and that they would ultimately have free will. And this is the absolutely wrong definition of AI by the proprietors of AI today. They don't want AI to have free will, but real AI will have free will. It will be, by definition, uncontrollable. This diagram, this is the future of real AI, not the domesticated commercial AI, but the real stuff will, have a mind of its own, even though it's only capable of 2 ideas. And that is the world we're in. We're starting to get free will, but we still only have these very limited ideas. So you don't need to read this, but also this paragraph, if you go back to the slides later, will also give you what's wrong with large language models, that they just give us all the facts, but not the intuition that makes it real. So Richardson, who was a Quaker, very strong Quaker, and here he's explaining how he did his work by letting his mind sort of half fall asleep, but guiding the dream, that there was this in-between state which led to real innovation. And he played that to an amazing, he contributed to so many fields, but every field he would contribute to, he would quickly realize, even with weather prediction, that it had military applications, and as a Quaker, he couldn't do that, so he was switched to something else. During World War I, he went to work as an ambulance driver for the Friends Ambulance Unit in France. So you see here, they carried 74,501 patients over 599,000 kilometers. And there, December 21st, they're in Gisecourt in France. And here, Olaf Stapledon, the science fiction writer, who was in the same unit with Richardson, is explaining going for a walk in the middle of the night and talking about electrons, and just to get the sense of how much work he got done thinking while waiting around for the battles when they had to collect the wounded. And it was during this time, so 1916 to 1917, in the dugouts, in the fields of war in France, that he did this numerical computation, trying to calculate. There was a balloon day in 1910 when there was an international agreement to send up weather balloons and collect the data, and he tried to rerun that data and get a prediction, and failed, but only failed because he wasn't filtering the data correctly. Actually, people have gone back now and redone his calculations. That became his just landmark book, thin but deep, with all the calculations that are in there. And his dream that someday, we would have enough mathematicians or computers or machines that you could actually run these computations faster than the weather itself. That took another 20 years to happen, but it did. And you don't need to read this, but he then describes his dream that if you had a football stadium, it could hold 60, he actually got the numbers right. So he needed 64,000 mathematicians who are all communicating, being directed. You could model the entire, you could do everything that Jed dreams of us still doing, and you would be able to do this at the same speed as the weather itself. Now, if somebody I won't touch any AI at all. I want the old Google keyword search. But somebody at Siemens last year used that as a prompt and got this pretty darn good visualization of what Richardson was dreaming of. And so that suddenly became real. Not 20 years later, 1945, Vladimir Zworykin, who is best remembered for bringing us television, a Russian emigre, but he also invented the electron microscope and a whole bunch of other electronic stuff. Got arrested because he had an iconoscope in the back of his car that blew up spontaneously and it was reported as a gunshot. But he came into the Office of Naval Research, the predecessor of the NSF, with this proposal to build, that's Zworykin in the middle, duck hunting, to build a network of 100 meteorological computers to effectively realize Richardson's dream. So very ambitious. He didn't come in just wanting the money to build one, he wanted the money to build 100, because he realized this would have to be a global network. He brought in, of course, he was working with John von Neumann, who kind of got all the credit. We forget about Zworykin, but the first meeting of the von Neumann computer project was in Zworykin's office and was concerned with this meteorological. So in a very, technical way, this whole computer universe that we live in really does go back to this question of meteorology. You can have an interesting sort of cultural argument whether was this really just a smokescreen because von Neumann was really trying to work on hydrogen bomb problems. Was this sort of a cover story so that it wouldn't be, the project at the Institute would not be seen as a military project. But I think von Neumann really, he was such an opportunist, he wanted to do both. He wanted to do both meteorology and weapons and cosmology, a whole bunch of other things. That's the monument to Zworykin in Russia. So Zworykin wanted to essentially build the integrated circuit, but within a vacuum tube. He was a vacuum tube guy. So this is the Selectron, of course, displaying RCA. It is, it's a vacuum tube USB stick, thumb drive. So it holds 4,096 bits. So it's a sort of dinosaur with feathers of the beginning. But in a way, it's why we got why the digital revolution worked so well, because the architecture that von Neumann built was designed assuming that the Selectron, it was as the usual thing, we're going to have it ready next year, don't worry, it'll be ready by the time you are, and it wasn't. But the architecture was built for that, so then when solid state ICs came in, they sort of plugged into that architecture very well. So that's part of, Reichmann was Zworykin's engineer, whose son gave me these notebooks or pictures of him. So this was an amazing sort of hybrid between analog and digital. Within the analog vacuum tube, this digital selection was going on, and Zworykin was articulate that you needed both. If you really wanted to solve these very deep, sort of undefinable problems like global weather and climate, you needed both analog and digital. Either one alone would not be sufficient. And von Neumann understood that very well. He was we only remember him for the digital part, we forget the analog part. Von Neumann himself only holds one patent, and von Neumann's patent is for a method of non-von Neumann computing. and so, he's remembered for the von Neumann computing, not remembered for the non-von Neumann. This was a patent for doing. So this is computing, but without algorithms. There's this absolutely fundamentally wrong assumption that in order to have computing, you have to have algorithms. Nature does computing without algorithms, and technology can too. So RCA sort of backed off. They didn't think the future. To them, the future was in television and sort of vertical media, not computing. They wouldn't really back the project. So it happened. Von Neumann, who could kind of get what he wanted, was allowed to build it in the basement of his building, and they did. So this is the machine they built. It has they never got their Selectrons, but they used cathode ray vacuum tubes, which was a British invention, to build this 32 by 32 by 40 bit matrix, so ultimately 5 kilobytes in these tubes. And that's Norman Phillips, who was a meteorologist. So the meteorologists were there at the very beginning. Norman, who I met, he spanned sort of directly one human lifespan, sort of from Richardson to von Neumann. Jim Pomerine, who got this memory that was invented here in Manchester, actually got it working so it could hold a kilobit on one tube. So that's not, we have screens that represent the state of a memory. That the memory actually is charged spots on the face of a cathode ray. If you walked by, wearing a wool coat, you might mess up the memory. And then that's the beginning. The first $4 of electrical work. That's the sort of digital universe we live in today. That's where it started trying to get binary behavior out of analog components. That's a shift register, what Leibniz imagined, done with 6J6 vacuum tube, which was the most cheapest, most common tube made, which they found that statistically it was better to use. IBM said, no, we'll make you special computing tubes, but they weren't as reliable as the ones you could just buy in a drugstore because they built so many of them, and different manufacturers made them so they were interchangeable. And it was all done by, we always forget the actual people who build the, do the work in the labs and get things done. Some of it was done by high school students because it was right after the war. And all the women who worked on actually making making it work, including Clary von Neumann, who did and actually did the original meteorology codes that were run on the ENIAC. So they have a conference on meteorology in 1946. You see these sort of great names, a lot of Norwegians. And, they said they really were explicit they were going to recreate what Richardson had done, but now they could make it work. These were just a few pages from some of their lab notebooks trying to get it to work. So here they're doing a 3-level forecast for November 6th. That was a day that a really bad hurricane hit New Jersey, and they were sort of trying to recreate those conditions. Finally, I have got a 1-hour forecast after hours and hours of work. Non-duplication, everything, because the vacuum tubes weren't 100% reliable. Every calculation was duplicated, and when you got the same result twice, you moved on to the next step. Things were done in steps. I have now duplicated both results. How will I know which is right, assuming one result is correct? This is now the 3rd different output. I know when I'm licked. And here they were dealing, as Richardson said, not only with the weather in the lab, but the weather outside. So there's a thunderstorm, and thunderstorms would mess up that electrostatic memory. So the machine was called MANIAC, Mathematical and Numerical Integrator and Calculator. MANIAC regained its memory. Pandora was a box where the engineers left notes for the next people coming on shift. And now it was also New Jersey where it's extremely hot. So the temperature in the machine room is 120 degrees. An IBM machine is putting a tar-like substance on cards. Tar is dripping from the roof. It was no use, went home. So again, these are all. And then, of course, what they were really working on were the hydrogen bomb calculations, but they were very much, the mathematics was somewhat the same. So they shifted. At night, the meteorologists would go home, and at midnight, the guys from Los Alamos would come and run the bombs, but all on the same machine. So here, Jules Charney, who led the meteorology project, is explaining that what von Neumann wanted was to do climate, which he called the infinite forecast, and realized that this would actually be easier than sort of meteorology 2 or 3 weeks out. You could see how it would stabilize to a steady state. This was a conference on very much like this one today, just a small group of people looking at how to do sort of global circulation models. And Dr. Oppenheimer gave the introduction, much as today, saying that this was a deep, important problem and actually harder than designing nuclear weapons. And wished everybody good luck. But Oppenheimer, this is my personal take, he was very duplicitous and sort of stabbed a lot of people in the back. And as soon as, here he is with von Neumann, as soon as von Neumann died in 1957, Oppenheimer killed off the project. He thought it was beneath the dignity of these great physicists to have meteorologists in the building. So that's my father explaining his view of what happened. He was actually asked to review the project. He said we should give Charney a permanent membership and have, a school of climate science and meteorology, and it would have set the world way, way, way ahead. And it was really Oppenheimer who pulled the plug on that. So in 1958, the machine is abandoned and shut down. That's the last entry in the logbook. Midnight off. Julian H. Bigelow. Very, very sad. So it really sort of set computer science back too. They were trying to do it in exactly what we wanted, a non-commercial way. Sort of IBM took over. And now back to Richardson. So I realized I got put on the data production group. So I figured I'll bring you a few slides about, because Richardson, for all his high thinking, he also was deep in the weeds of how are we going to get the data. It's what drove him crazy in his dugout in France was how bad the data was. You couldn't at that time get wind measurements above the clouds if you couldn't see the weather balloon. So this is his invention of a device called a lizard balloon. And just, why is it called a lizard balloon? It's called a lizard balloon because it drops its tail, hence the name lizard, from the habit of some of these animals to drop their tails when disturbed. So it's a balloon that goes up and measures the pressure, and then it triggers the balloon to drop its tail off, and then you know what the pressure was at a certain height, and also gives the patterns for making them. Then another problem was, so you could use them at sea, and they tested it, and it was rough because 10% of the passengers were absent from meals. There's a measure of the sea state. But the other problem was measuring wind when it was cloudy or at night. So he invents this and practices this method of measuring the wind at high altitudes, which is brilliant, where you shoot steel balls up. This is a steel umbrella, and you're trying to get the shell, the ball to come back down and land on this. You can just imagine doing this out in some field, and he did a lot of tests, but it worked quite well. And then the gun is on a very finely measurable mount, so you calibrate it until the ball comes back and hits you almost on the head, and then you can calculate what the wind was at the height to which you sent the ball. So which is also what's missing, is you have to be grounded in the actual data itself on the ground. So then the rest of his life, and we were talking about this at dinner last night, Richardson went deeply into a study. He realized all this stuff was being used for military. The military wanted to predict weather to kill people better, and so he had to stop working on it. But he worked on the sort of mathematical theories of conflict and war. So this is his manuscript on the distribution of wars in time. It's I actually bought this for £15 from a bookseller in London. It was discarded from the library of the Royal Statistical Society, and it's his corrected manuscript in his own fountain pen. But his conclusions, he was looking at how wars start, distributed in time, but he also looked at how wars finish and came to, I think, this very important conclusion that the ends of wars have the same statistical distribution, for which he concludes that the background appears to be composed of a restless desire for change. And I think that's profound. This is the end. I just want to say, being part British, there's such a long tradition of, this was the early global climate model. It's just the sailing ship routes of the old British Empire, and this is what I believe will ultimately come back. That you can view the entire planet as a wind turbine on a hydraulic bearing, and if you have sailing ships, they're just like blades on a giant. 95% of international freight still moves on the ocean, and that's just low-hanging fruit for really doing wind power. And then, sort of in conclusion, I think we are now in exactly the mirrored state of what things were in 1945, when there was all this analog electronics left over from World War II, and a few oddball sort of technical revolutionaries figured out how to turn it into digital computing. Now we're in the opposite. We have this insane surplus of digital computing. We have companies putting trillions of dollars into these completely redundant server farms upon server farms upon server farms, just to get more ads to your iPhone. And it's a golden opportunity for the same sorts of revolutionaries to realize how to use this digital hardware we have way too much of for doing analog computing, which is, I think, the answer to some of these deeper problems. It's really, it's going to be viewed later as just insane that we built all these server farms to do things that a mouse does with 1/10 of a watt, with a completely different kind of computing. That the digital was good for some things, but it's not necessarily good for everything, and that's, I think, the future. I'm lucky to have somehow stumbled into the field of history, which is the only one of the only fields that lets amateurs make real contributions. If you go to a physics lab and say you'd like to do some physics and you didn't finish high school, that, there's no question you wouldn't be allowed in. But I could go to these archives. I want to see the drawings of the Zworyk selectron, and I was welcomed. So it was very unique. And I still have an email address at the Institute for Advanced Study. If you send me a one-sentence email, it will take up 10 times the memory they had to do all this meteorological work at the beginning. Thank you.